Welcome to 511. Those of you who don't know me, I'm Michael Deutsch. Does everybody have one of these pieces of paper? You don't really need one, but because what is here is the only piece of paper that I will be handing out during the semester. It is a printout of the website of the class. And this horrible URL is the link, but the link is there on the department's website. You just go to the class's homepage, for the schedule of courses for the department, and you look for 511. It's linked there. It's also linked on my website, my classes. I think I'll double check that, and I'll send you an email too. So, because it's essential that you get access to all the materials to the class that will be distributed through the class website. So that includes the all-important problem sets, as well as class notes that will be distributed. And we'll do a little experiment here where we have Dr. Rio Frio there, the cinematographer. Sorry, the Golden Globes already came out. You missed your opportunity, but there's always 2012. With this big of a class, I don't know, everybody's head will, make a cameo. We'll see how it goes. Right. So the TA for the course is Shufeng Zhang, and I'll talk to him about setting up an office hour. There is a problem session for the course that's currently scheduled on Wednesdays at 12:30 in room 5. Now, in room 5, I don't know if we're going to fit. So we may have to rearrange that, but that's what's currently going on, okay? We'll think about a potential alternative if necessary. And in addition, I'm planning to hold at least one office hour, and Monday is the best day for me to do that. And I'm completely flexible other than from 4 to 5 where I have a meeting. So, what time would work? We have a huge class, so that may not work, but who can't do it from 9 to 10? One person. From 10 to 11? 11 to 12. Okay. So, and afternoons, most people have TA. Noon to 1, who can't do it noon to 1? Oh, noon to 1. Bring your lunch. Okay.
This is on Wednesday?
Monday.
Oh, Monday.
Monday, noon to 1. In my, we'll say in room 30, which is a room that. All right? So that will be just my office hours. Let's see, more course administrative. So, let's see. So the course, in terms of the course requirements, first of all, everyone, of course, should have had a good undergraduate, junior, senior level course in electricity and magnetism, kind of at the level of Griffiths. In addition, you all should have had the equivalent of math methods for 66 or equivalent, okay? This course, some years ago used to be a year-long course. And, the first semester was statics and the second semester was dynamics. And the first semester was basically a math methods course. It was, you know, how many different ways can you solve a boundary value problem with a beach ball with every other wedge at a different voltage and what's the electric field inside, that kind of thing. So some years back, it was decided that since we already have math methods, that's the place that you learn about special functions and boundary value problems and so forth. And this semester, one semester course, thus, will have a fairly accelerated review of electro and magnetostatics. And then we'll spend the vast majority of the time talking about electromagnetic waves and radiation, and hopefully special relativity as well. Okay? It's a good idea for you, if you haven't studied for your prelims in EM, which I'm sure everyone has, passed them, then it's a good idea to make sure you review your undergraduate course in EM, because I'm really going to be assuming that's right there at your fingertips. Let's see, what else can I say? Well, you know, the textbook, just because it looks nice on your shelf, is the famous J.D. Jackson book, now in its third edition. I actually had Jackson as a professor at Berkeley. Oh, we're better I didn't have him for EM, I had him for quantum mechanics. And then I also had, at the same time, I had, you know, the EM course. So it was like all Jackson all the time. And I used to have a lot more hair. So, I'll show you pictures sometime. Anyway, we won't be following the book in any sort of very systematic way. I have, as many of you know, my own idiosyncratic ways, and so you're forced to sit through them. But nonetheless, I mean, there's a tremendous amount of excellent resource here, and so this is the book. There are a few other books are mentioned as possible references, and you know, select them at your desire. As far as the grading goes, the grades are going to be assigned based on combinations of problem sets and exams. And WIM, no, just don't remember them. We'll have problem sets pretty much every week. And, you know, this is boot camp for physicists, so start practicing walking through the tires and doing the monkey bars, because that's what's going on here. Those of you in the military, I'm sorry, you probably think it's part of the boot camp, I'm sure it is. Beyond that, there will be 2 take-home exams sort of sprinkled into the semester, and then there will be a final. All right? Let's see. So, you know, what's written here is what's called a tentative syllabus. We'll see how far we get. Hopefully we'll get through it all. I have a kind of schedule, you know, like you have fantasy football, I have fantasy syllabus and fantasy lecture schedule. Let's see how we do. All righty? All right. Does anybody have any general questions, concerns?
You don't mind us emailing you with problems that we have with problems, correct?
I don't mind emailing me, but I don't guarantee instant responses relative to, you know, some questions, specific questions about, I'm not sure how to do this problem, so forth. We'll do our best to answer those. We do have office hours, TA will have office hours, and we have a problem session. And if I am available, I'll do my very best. So yes, feel free to email me, but I don't promise instant response. I'm on Facebook, but forget it. Anybody else have other questions?
You say this is, the textbook is going to be, it's not kind of a regimented.
That's right. So I will, when I assign an assignment, I'll reference relevant sections of Jackson that are coordinating with what's going on. But in addition, I will be distributing my notes. So they'll be kind of the main text. But for those of you who've been in my course, you can talk to them what that's like.
As far as lecture goes, lectures come from a section of the book? Or
No.
No? But will it be corresponding sections?
Yes. Sometimes yes, sometimes no. If there was a book that did exactly what I wanted to do, well, I would write it. That's the problem. Yes.
So presumably the questions on the homework would not be from the book?
Sometimes they will be.
I mean, as in, will you reference?
I will assign a problem from Jackson
Right.
from time to time. Yes. So it's not that this is completely disjointed, what we're covering, what's in the text. I mean, EM is pretty standard stuff. There's really kind of, that's why, there's the book. But, there's plays on the theme. And, so mine will be in D minor. Anybody else have questions, concerns?
So we should pay more attention to your notes than to Jackson's.
Yeah, I mean, the way you should pay attention to the homework. And, the way I look at it, when I want to learn a new subject, what I do is I try to get a few different books simultaneously. Because if I just read one book, I'm kind of just getting a reflection of exactly what that one individual interpreted and thought about. And in order to really learn a subject, you need to make it your own. You need to hear your own voice understanding it rather than the voice of Jackson. And so the way for me personally when I learn is I eventually make this Venn diagram of all the different approaches, and then I see what's kind of intersecting within them, and then I kind of understand that this is really important. So my point of view on this is that you should do both. You should read Jackson, you should pay attention to lecture, notes will be re-emphasis of lecture, and through the combination of those, something will emerge that will be your understanding of the coursework.
Do you also post your notes online?
Yeah, they are. So that's the point. So, right now, if you look, it says download one. So that's already available. And so they'll be available online. And they'll generally be scanned, handwritten notes. This first one happens to be typed. Because, at one point, when I had just a tiny bit more hair, I was ambitious and I did type them up, but I'm old now. Maybe someday. I don't generally, as you will learn, all of my many idiosyncrasies, generally the notes won't be available before class because it's my view that you learn better by taking your own notes and paying attention than reading. And if I just give out the notes, people tend to not be, if you want to read them, that's fine, and not come to class, that's your prerogative. Attendance is not mandatory. But if you're coming, I just prefer people, you know, engaging with me than reading the notes. All right? Very good. All right, so we'll get the show on the road. Everybody should shut their cell phone off. Mine's off, good. That's it. So, subject of electricity and magnetism, you know, to me, it's really the most beautiful subject we have in physics, and it's really a representation of the best of the scientific method. I myself, my research is in quantum physics, and well, you know, quantum physics is cool. Quantum physics is ugly. You know, it's got all this hand waving and all this, you know, kind of magic of sorts that seems to come out. And with electricity and magnetism is in some sense the most pure of physics theories that we have. It's the basis of modern field theory. It's what Einstein was hoping to build on for his version of a unified theory back at the 100 years ago or so. You know, what I mean by this is that when we think about the scientific method and physics, we have some interplay between experiment, or what you might call empirical data, and models, what we might call theory. And the history of EM shows the interesting feedback between these, in which, you know, if you think back historically to the 16th, 17th, 18th, 19th century, people, you know, shocking frogs' legs and sticking lodestones in coils and kind of getting a sense of that, of electric and magnetic phenomena and the connections between them, which led, of course, Faraday and Ampere and others to develop mathematical models in which to describe the data, how am I writing? Yeah. Can't spell. Okay.
This is out in front of the city. ICAL.
Thank you. So one of the important aspects of this in the scientific method is, of course, we also have within our thinking about our models, we think about consistency. As well as thinking about conjectures based on physical principle. So, of course, we know historically in this development, once we had some of these models, Maxwell looked carefully at these mathematical models and realized that there were inconsistencies in that mathematics. In particular, the question of conservation of charge was inconsistently modeled according to the laws of Ampere and Gauss etc. And from that was able to deduce purely from theoretical perspective that the equations need to be modified in some way in order to account for that inconsistency. And from that developed the idea that the electromagnetic wave was related, or this one and the same thing, as optics. That's quite amazing. I mean, that's quite a triumph for physics. And of course, that in itself isn't the whole story. It's when that is fed back and one can do the experiment. It hurts the experiment to show that radiation was formed, radio waves were formed from oscillating currents, and that is the triumph there. Of course, we have other examples of that. An important example is the issue of the notion of the speed of light, which in this case, the empirical data was the Michelson-Morley experiment, which gave the null result that there was any difference in the speed of light in different inertial reference frames. And of course, that led Einstein to conjecture that, well, maybe the speed of light is the same in all reference frames. And if that's the case, what are the implications? So all of these pieces together gives us such a theory based on as pure a logic as you can possibly get. And it's for that reason I'm always really excited. I haven't taught this course in many years, and I love it for that reason. Okay. Now, there is one, where I said how beautiful this is and how excited I am about it. There is one thing that's particularly ugly, and that's the question of units. So, when we electricity and magnetism, we start from the basics of the empirical aspect of electricity and magnetism. We're talking about the basic observation is that there are forces on and due to charges and currents. That's the foundation. So we have Coulomb's law. Coulomb's law tells us that if we have two charges with some distance between them, and I can define a coordinate system with some origin, which is some potentially other place. So the position of charge 1 we'll call x1, position of charge 2 we'll call x2, r21 is then x2 minus x1. Then the force on charge 2 due to charge 1 is proportional to the product of the charges, the distance between the two charges squared, and the direction of the force on 2 due to 1 is in the direction, the unit vector between them. Okay, that's of course Coulomb's law. Now, we have the issue of units here. And so I said it's proportional to all these things, and there's some constant called K1 that, in some sense, relates the units of distance and charge to the units of force. Okay? Similarly, we said forces and charges. This is Coulomb's law. This from a magnetostatic point of view. Now, I don't know, Carlos, how this is going to work. This is going to be,
Oh, we'll try.
should I come a little closer?
It's fine.
All right, we'll try it. So we have the Biot-Savart law, which, I'm thinking, I don't know, guys, should we, given the size of this class and the angles of things, because no one's going to see this, right? You guys over there, over there. Now, if I write in the central board, is this doable? Okay, so we're going to skip these two boards, and I will go down 3 times. All right. Biot-Savart. All right, so the Biot-Savart law tells us about the forces between currents that are steady. So if I imagine some long wire and some current flowing in it, and some other wire with some current, and I'm just drawing some little chunk of that current, and there's some distance here, so this is wire 1, this is wire 2, again you have the vector connecting them. We have a little current here I'll call VI1, or let's see, keep my notation straight here. Yeah, that's the way I want to do it, right? So there's a current I1, there's a little unit vector, or not unit vector, differential vector of length, dL1. And there's some current here, I2, dL2. Then the force on this little chunk of the wire, dF, due to the little chunk 1. Well, unfortunately, it's a magnetic field, so we got cross products galore. So we have I dL1. This is force on 2. Yeah. So it's proportional to these two little elements. We have force on 2 due to 1, which is I1 dL1 cross R21 hat over R21 squared. That's correct. And again, this is proportionality. And that proportionality constant we'll call K2. All right. We'll come back to what choices we should make for those constants in a moment. So, of course, we can treat and think about electro and magnetostatics. We can do so just in the context of thinking about action at a distance and forces. And that's perfectly fine, and we can get everything right that way. But it is very fruitful, as you know, and becomes extremely important in the context of dynamics to abstract and think about the notion of the field. So what we do is we say, well, if this is charge 2, the reason that charge 2 is experiencing some force due to charge 1 out here is that charge 1 produces some local electric field. So this is the electric field due to charge 1 at the position of charge 2. And the definition of the field, as you know, is the force per unit charge. If we think about a little test charge here, to experience what its force is, we divide by that charge and we get the field. So the force on charge 2 is proportional to that charge, and the electric field at position of charge 2, in this case the electric field due to charge 1. Of course, we are ignoring in this case the self field. That's a whole another ball of wax of what the fact that this charge itself produces a field, and how the heck do we deal with that? Maybe we'll come back to that at the end of the semester. So from this, if we take our force law as given over there, this defines the unit of the electric field as well with respect to the same constant K. So the electric field due to charge 1 at position charge 2 is then equal to that same constant proportional to charge 1, R21 squared R2 hat. Of course, the unit vector is equal to the vector divided by its length, so sometimes we will write this as the vector R21 divided by the magnitude cubed, because one of those absolute values gets absorbed in to give us the unit vector. And that is sometimes written out more explicitly in terms of x2 minus x1 divided by the magnitude of the vector cubed. K1, excuse me. Okay? Similarly, we have the notion of the magnetic field. So the little differential force on this current in this case depends on what the local electric field is due to 1. I'm sorry, the magnetic field, pardon me. And that magnetic field here is related to this cross product, right? So we have this vector going in this direction. The cross product tells us then that the local magnetic field is out of the board. This is the magnetic field due to a little d1 due to one of these guys over here. And then there therefore is a force which is in this case attractive, right? So there's a force dF on 2 due to 1. So this gives us a definition again. So we have the little differential force due to 2 on 1, I dL2 cross into the magnetic field due to 1 at the position of that little chunk of wire. And from this, we have a definition of the magnetic field based on the Biot-Savart law. Now, we have yet another constant to choose because we have current, which is charge per unit time. We have distance. We have electric field. There's no necessary reason what the choice of the units of magnetic field don't have to be tied to the same definition of force. And so the most general thing we would do, sort of an extra constant we have, is to define dB, in this case, to put a constant here, a new proportionality constant. And so from this, what we see is that the magnetic field depends on this ratio of whatever constant we chose for this constant K2, this new proportionality constant, which is called alpha, and then all this stuff. Okay. Oh, I should mention one last thing before we then get into what our choice of these constants is. Of course, in the picture that I drew over here, the force, if I imagine this to be an infinite wire, the force on these becomes infinite. We integrate over the whole wire. So typically when one thinks about this problem with very long wires, what one does is one looks at the force per unit length. Okay? So if I integrate this over all distance, I get the local magnetic field, which is finite. But then the local magnetic field exerts a force per unit length, which depends on the distance between the two wires. And that force per unit length is equal to K2 times 2, the total current I1, I2 divided by the distance. Okay, so now we need to, the question is, for the question of units, the question is, oh, I shouldn't have come into this board. This is going to be a challenge for you working through this because you put people in the corner there. Sorry. The question of units is, what do we choose for K1, K2, and alpha? Once we choose these three things, we've fixed the choice of units. Okay, so let's try it. Yes, sir.
So this is like jumping the gun a lot. But just we don't need to worry at this point about, because there's going to be, like, won't there eventually be some relationship between those to get like the speed of light or something?
Right, we're going to mention that. They're not unrelated quantities. So we'll get to that in just a moment.
Okay.
In fact, let's say something about that right now. Let's just look from dimensional analysis ask what is the unit, not in terms of the number, but in terms of length, distance, etc. The ratio of K1 to K2. Assuming these are both forces. So the force is in units of mass times acceleration, so that's fixed. We have Coulomb's law over here, which depends on distance squared, depends on K and the two charges. Whereas this thing depends on K2, the two currents, and the two distances. These two things are common in both of these expressions. We have this and this common. So the ratio of K1 to K2 must be related to the ratio of the charge to the currents times the distances, right? So whatever the number is that we choose for these two things, the ratio of these two things must be of the unit of some velocity squared. Then K1 and K2 both convert currents and charges to forces. Is that clear? And in fact, as Jacob mentioned, this number is nothing more than the speed of light squared. Now, that is amazing. That's just from purely magneto and electrostatics. We haven't even said anything about radiation. But it's built in. It's baked already in there. So C is the speed of light. So whatever units we choose for K1 and K2, their ratio must be such that K1 over K2 is 1 over the speed of light squared. Okay? All right, so now in the ancient days of the 19th century, there were two standard choices for these units. Okay? First of all, in the ancient days, already we got into the metric system, but the metric units that were standard were, instead of thinking about what the SI units, which came a little bit later, CGS stands for centimeter gram second. So first of all, these are the standard units of the CGS system. And so there were two sets of units. First of all, in the arcane system is to choose alpha equals 1. Period. Okay? So if alpha is 1, then we have two choices. One is called the ESU system, and the other is the EMU system. Electrostatic unit and electromagnetic unit. The ESU chooses K1 to be 1, in which case K2 has to be equal to C squared. Right? So in this set, this is a particular choice of units. One of the things that you notice about this unit is that if you choose this set of units, firstly, that the unit of charge is related to length, time, and mass. They're related because if you look at Coulomb's law, let's come back to the EMU. If you look at Coulomb's law, then Coulomb's law says that force is equal to charge squared over distance squared. Right? And since force is equal to mass times acceleration, and this is charge squared over length squared, then charge is related to these other things, right? Charge, then the unit of charge is equal to the square root of the unit of mass, the unit of length cubed over time squared. Okay, this unit of length is called the electrostatic unit. Unit of charge is the electrostatic unit, and then the unit of current is 1 ESU per second. Okay. Alrighty. So that's one set of units. We never use these, but I want to go through this because I want to see where the hell these units come from. Right? It's not something that just, you know, Moses came down. It wasn't the 11th commandment. There shall be epsilon not. There was a reason. Maybe not. Oh, by the way, the unit in CGS units, the unit of energy, or the unit of force, is a dyne, and the unit of energy is an erg. Erg! Now, of course, these are just other CGS units, right? I mean, other metric units, because it's just a question of whether you're using meters versus centimeters. So there's just factors of 10 that convert these guys. An erg, I remember, is 10 to the minus 7 joules, and a dyne is 10 to the minus 5 newtons. Okay. The EMU E mu, is just the opposite. You choose K2 to be 1, in which case K1 has to be 1 over C squared. Okay? And in this case, this defines the unit, instead of charge, defines the absolute unit, a new unit, which is, or the unit that relates charge to length, time, and distance as what's called the ab amp, the absolute ampere. So the ab amp is the, 1 ab amp must have real charge. Let's see what we got. Excuse me. So the ab amp is defined such that if I look at the force per unit distance, which we said in this case with K2 is equal to 1, the force per unit distance then is twice I1, I2 over the distance squared. If I have 1 ab amp in each 2 wires, with 1 ab amp each in the wire, then if I have 1 dyne per, is the force such that the force per unit, is the current such that the force per unit distance is 1 dyne per centimeter when the distance is equal to 1 centimeter and the current is 1 ab amp. Okay? So, oops, sorry, beware, he says. All right. So it's defined in terms of this is the defining relation between force and current. If I put 1 ab amp of current in each wire, I separate those wires by 1 centimeter. If I get 1 dyne per centimeter, that's the standard current. And then an ab coulomb is 1 ab amp in a second.
So why is it called, sorry,
Why is it called ab?
yeah, it's absolute.
It was
What is
absolute,
that?
yeah, because this was ab in terms of these extensive absolute units. The reason was, so now we're here we are in industrial England, where the telegraph is being developed, and the ab amp was a little bit too much current for standard practices, and so they defined, these names of ab amp came later and so forth. 1 amp, or an ampere, is 1/10 of an ab amp. Okay? That's just because that wasn't very practical. This was the practical unit for telegraphs in the 19th century. That's why we're stuck with the amp. Because that's, the wires in telegraphs, the ohm was defined because of whatever wire they had. It's not from some fundamental physics of any kind.
Really, 1 amp is pretty big. For
It is.
telegraphs?
It's not practical anymore. This was practical for telegraphs. Yeah. It's a big current.
Yeah.
Yeah.
Telegraphs also use like a lot lower voltage, so it's not as much as it would be today.
But this is not, so we're kind of coming to a point which is that, is this really, there are standards, ultimately as physicists, as we know, if you're analyzing a problem, what you really want to do is think about what are the characteristic units of the problem you're working on and make the problem dimensionless and tie the units to the problem at hand rather than some piece of metal sitting in France. But on the other hand, we ultimately need to reference to so these things have historical background basis. Okay, so these are the sort of most the least, in some sense, contrived set of units. You just set alpha equals to 1. There is this constraint between k1 and k2, so you choose one of them to be 1, and then the other one is c squared, or 1 over c squared. Okay? Now, there's one problem with this set of units and why none of these are used anymore. And because alpha equals 1, the unit of the electric field and the unit of the magnetic field are different, right? Because the unit of the electric field and magnetic field are related by this. If alpha is 1, this is not a charge. This is a charge times a velocity, right? So in EMU and ESU systems, electric field and magnetic fields have different units. And that stinks. I want to come back here and just read you a passage from Jackson. So, favorite bedtime story. Chapter 11, special relativity. Beginning with chapter 11, we employ Gaussian units instead of SI units for electromagnetic quantities. Explicit factors of C appear in a natural manner in these units, making them more appropriate than SI units for relativistic phenomena. So why the heck did you use SI units for the first half of this book? We're not going to do that. Because SI units aren't the appropriate physical units. They're really appropriate more for electrical engineering. And somehow, and this is the editorial review, the fact that halfway through the book you had to switch units tells me something. So we're going to stick with what are called Gaussian mixed units throughout. And you are going to have to learn to speak 2 languages in this course at the same time. All right, so we're going to, we'll come back to this. There's this, so we had ESU union, we have yet a third set, which are called Gaussian mixed CGS. The fact that it's CGS and not, kilograms and meters is not so important. The important point is that in Gaussian units, Gauss obviously was behind this, the electric field and the magnetic field have the same units. As they should, because they are just different visions of one another in different reference frames. In order to do that, what we choose, alpha has to have the units of 1 over a velocity, so that you can cancel out the distance and the 1 over time that occurs in the relation of force to charges. So alpha is 1 over c. And so that's why it's called mixed, is that it kind of mixes the EMU and ESU kind of system. In this system, we choose K1 equals 1, just like in the ESU system. So Coulomb's law appears as Q1, Q2 over R21 squared, R21 half. That's it in these units. The force law here, now, because alpha is 1 over c, the Biot-Savart law, so this is Coulomb. The Biot-Savart law, I guess I must go up here, huh? IEL over c cross. This is the force on 2. B1. Okay. we will get used to these things over time. Okay. Now, of course, there is yet a fourth set of units, the one that is the standard, really, SI, NKSA. Now, this is sometimes called rationalized, although I find it quite irrational, NKS units. And in this set of units, you choose K1 to be the very intuitive 1 over 4 pi epsilon naught. And K2 is mu naught over 4 pi. Of course, K1 over K2 is equal to 1 over mu naught times epsilon naught, which, as we all know, is 1 over the speed of light squared, as it must be. Why is this called rationalized? There's actually a fifth set of units, which is rationalized Gaussian units, sometimes called Lorentz Heaviside units, which is what, if you read, for example, Sakurai's relativistic quantum mechanics book, that's the units he uses. And the rationalization here is the dividing by 4 pi. And that's so that you get rid of 4 pi's that show up in Maxwell's equations. We'll come to that in a moment. But I like those 4 pi's in Maxwell's equations. They tell me something about geometry. Why would I want to get rid of them? Because you're lazy, you don't want to write 4 pi? Come on. That's why that's done. That's why it's divided by 4 pi. Yeah.
So SI is arcane?
Well, our SI is what, this is
Well, alpha's
some
one.
internationality. It's not arcane, it's, in the sense that arcane, I mean, it's like not used anymore.
Well, alpha's 1. I don't know.
Yeah, that part is the same, but
So we don't call it arcane?
I don't know.
Okay.
No one. It just meant those are old units that no one used
Oh,
anymore.
I see.
These two sets of units are used. I mean, Jackson uses both of these in his book. Now, what is epsilon naught and what is mu naught, and how are they defined? Well, here's how they're defined. And now, actually, at least they have it. I think the system of units, you know, what used to be called the Bureau of Standards is now called National Institute of Standards and Technology. They're redoing all these things, kind of tying them to more fundamental quantities. But this traditional definition of the amp is the same definition. So the idea is that if I put one, so why is this got called MKSA? Because now we have a new unit, the amp. Okay, that's a new thing. And that these proportionality constants relate force to current through mu naught. Okay, and the way it's defined is that the force per unit distance between two wires with 1 amp each separated by, or I should say the force, yeah, unit distance separated by 1 meter equals 10 to the minus 7 newtons per meter. Where the heck did this 10 to the minus 7 come from? Well, it came from this, because this was the natural definition when this was 1 to ab amp, and this shouldn't be squared, pardon me. Erase that from your notes. This was not, it should be equal to 2 times that, right? Because it's 2 times 10 to the minus. This is equal to 2 dynes per centimeter. The 2 dynes per centimeter is this amount. Okay? So, with that, we then define mu naught is equal to 4 pi times 10 to the minus 7 Newton times newtons per amp squared. That's the definition of mu naught. So mu naught is not a unit. The other thing that's defined is the speed of light is defined as 2.98 blah 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 10 to the minus 8 meters per second.
I mean, 1068, not minus 8.
Oh, yeah, that would be really bad. And then, of course, epsilon naught is defined through this as epsilon naught is equal to c squared over mu naught. Okay. All right, so we have different sets of units. The set of units we will use fairly exclusively in this course are the Gaussian mixed units. One of the reasons that I like this is one of the tools we have in doing at least theoretical physics is dimensional analysis. Kind of look at the problem, are the units right? Who the heck knows what the units of mu naught and epsilon naught are? You know, can you convert farad meters to grams? I mean, I don't. What are the units of magnetic moment? Magnetic dipole moment? Who can tell me? Yeah, exactly. I know. The units of, well, in CDS units, they're the same units as electric dipole moment. What's the unit of electric dipole moment? Well, it's charge times distance. And so that's the same thing. So I can check. Oh yeah, I left out a C. So let's write down Maxwell's equations. In Gaussian units. So we have Gauss's law, Gauss. I used to love the old Deutschmark. You know, I think it was the Deutschmark before the euro. They used to have one of the bills had Gauss, had one of their, I don't know, 20 Deutschmark or something, and it had the Gaussian on it, it had the right normalization, and, it was great. You could pull it out. You're pretty much, I'm just got my money, sorry. All right, Gauss's law. Gauss's law. Del dot E is equal to 4 pi rho. 4 pi is right, because 4 pi is all about the solid, this 4 pi steradians. We're going to want to get rid of that.
So the 4 pi's that will come in as a result of this are from with sphericals.
Exactly. So you're integrating over a sphere. There are 4 pi steradians. I mean, this is really 4 pi times k1, right? And k1 is 1. If it was 1 over 4 pi epsilon naught, then you would have rho over epsilon naught. You got rid of that 4 pi. The lonely equation, because it has no name. Del dot B is 0. No magnetic monopoles. We have Faraday. Del cross B is equal to minus 1 over C dV dt. And Ampere. Del cross B is equal to 4 pi over C J plus 1 over C. Now, let's just take a look at this and just think about the dimensional analysis of this. One thing, I can look at this right away and know that I got my C in the right place. Why? Well, in Gaussian units, the electric field and the magnetic field have the same units. The gradient is a derivative. It's 1 over a length. And so C times T is a 1 over length. Cool, did that right. Similarly, del cross B, 1 over C dV dt, I got the right thing. Also, if del cross B is rho, well, this is a derivative of a field is a charge density, then I got my C right here because a current density is a charge density times a velocity. So this is like rho times V. And so if I divide by C, yeah, I got all my C's right. This is cool. Let's just for fun write it, well, for fun, put this as in SI units. Del dot E rho over epsilon naught. Del dot B is still 0, that's good. Del cross E is minus dV dt, and del cross B is equal to mu naught J plus 1 over mu naught epsilon naught dt. Which one do you like better? Probably this one, as you know this. Now, if you want a little bit of a shorthand, you can, a little bit of a trick for conversions between SI and CDS when it comes to statics is, for electrostatics, since K is 1 in, K1 is 1 in Gaussian units, and 1 over 4 pi epsilon naught in SI units is to make the substitution epsilon naught goes to 1 over 4 pi. And for magnetostatics, mu naught over 4 pi goes to 1 over C. All right, so this is discussed in some detail in the appendix of Jackson, a good fraction of it, and might just take a look at this. I think it's important to speak a number of different languages, and you will see, when it comes to physics textbooks as well as research that's done in this area, it's kind of all over the map. And so really you need to be bilingual at least. You can forget about Coptic, arcane languages like EM511. All right, so I think we'll call it quiz for today unless anyone has any other questions. Oh, I guess there's one last one. Homework will generally be due on Fridays, okay? So what I will do is Fridays, the homework will appear on the web. I'll send an email, let you know it's available, and then it will be due in the grader's mailbox, and Jay in his mailbox by 5 o'clock. Okay? Actually, I'll probably say 3 o'clock because I don't want you guys to go close. Yeah.
I'm gonna put you on the spot.
Okay.
I think it'd be cool to see those equations with the k's in there and the alphas. Could you?
Right. Well, they don't appear. The alphas don't appear here.
Oh.
The alphas appear actually in one place. The alphas appear in the force law. So I guess I should write that down. The force law in the relationship, you remember Maxwell's equations relate the charges to the fields. But the Lorentz force law tells you what the force is then on charges and moving charges. In SI units, the force is equal to QB cross B. Again, note here, you see explicitly, if I have electric and magnetic fields that are on the same length, it's only when the charges are moving close to the speed of light that magnetic forces are of equal strength or of comparable strength to electric forces. It's another sort of intuition. We know, generally speaking, magnetic forces are tiny compared to electric forces. That's explicit here. So now the question, Brad, is what is this? So this would be 4 pi k1 rho over here. This would all be multiplied by k2. And this would be multiplied by Faraday law. It's a good question how the heck that would come in. Alpha, I think this is equal to minus alpha, the relationship between E and B. So in CGS units, alpha is 1 over C, K is 1, K2 is then equal to mu naught over 4 pi, yeah, that all works in this case. So these, and then the max, and then the other relationship here, yeah, I think this would be, there would be QE plus B cross alpha B. So that's the most general form. And you would put in something for alpha, K1 and K2. And you get those equations. Phew. All right. Have a good afternoon, everybody. I'll send you all an email. Is everyone registered for the class? And boundary value problems and so forth. And this semester, one semester course, thus, will have a fairly accelerated review of electro and magnetostatics. And then we'll spend the vast majority of the time talking about electromagnetic waves and radiation, and hopefully special relativity as well. Okay? It's a good idea for you, if you haven't studied for your prelims in UNM, which I'm sure everyone has, passed them, then it's a good idea to make sure you review your undergraduate course in UNM, because I'm really going to be assuming that stuff right there at your fingertips. Let's see, what else can I say? Well, the textbook, just because it looks nice on your shelf, is the famous J.D. Jackson book. now in its third edition. I actually had Jackson as a professor at Berkeley. Oh, I didn't have him for EM, I had him for quantum mechanics. And then I also had, at the same time, I had, the EM course. It was like all Jackson all the time. And I used to have a lot more hair. So, I'll show you pictures sometime. Anyway, we won't be following the book in any sort of very systematic way. I have, as many of you know, my own idiosyncratic ways, and so you're forced to sit through them. But nonetheless, I mean, there's a tremendous amount of excellent resource here, and so this is the book. There are a few other books are mentioned as possible references, and select them at your desire. As far as the grading goes, the grades are going to be assigned based on combinations of problem sets and exams. And WIM, no, just WIM. We'll have problem sets pretty much every week. And, this is boot camp for physicists, so start practicing walking through the tires and doing the monkey bars, because what's going on here. Those of you in the military, I'm sorry, you probably think it's part of the boot camp, I'm sure it is. Beyond that, there will be 2 take-home exams sort of sprinkled into the semester, and then there will be a final. All right? We'll say in room 30, which is a room we have access to. All right? So that will be just my office hours. Let's see, more course administrative. So, let's see. So the course, in terms of the course requirements, first of all, everyone, of course, should have had a good undergraduate, junior, senior level course in electricity and magnetism, kind of at the level of Griffiths. In addition, you all should have had the equivalent of math methods for 66 or equivalent, okay? This course, some years ago used to be a year-long course. And, the first semester was statics and the second semester was dynamics. And the first semester was basically a math methods course. It was, how many different ways can you solve a boundary value problem with a beach ball with every other wedge at a different voltage, and what's the electric field inside, that kind of thing. So some years back, it was decided that since we already have math methods, that's the place that you learn about special functions. And, welcome to 511. Those of you who don't know me, I'm Michael Deutsch. Does everybody have one of these pieces of paper? You don't really need one, but because what is here is the only piece of paper that I will be handing out during the semester. It is a printout of the website of the class. And this horrible URL is the link, but the link is there on the department's website. You just go to the classes homepage, for the schedule of courses for the department, and you look for 511. It's linked there. It's also linked on my website, my classes, I think. I'll check that. And I'll send you an email too. So, because it's essential that you get access to all the materials to the class. They'll be distributed through the class website. So that includes the all-important problem sets, as well as class notes that will be distributed. And we'll do a little experiment here where we have Dr. Rio Frio there, the cinematographer. Sorry, the Golden Globes already came out. You missed your opportunity, but you know, there's always 2012. With this big of a class, I don't know, everybody's head will, make a cameo. We'll see how it goes. Right. So the TA for the course is Shufeng Zhang, and I'll talk to him about setting up an office hour. There is a problem session for the course that's currently scheduled on Wednesdays at 12:30 in room 5. Now, in room 5, I don't know if we're going to fit. So we may have to rearrange that, but that's what's currently going on, okay? We'll think about a potential alternative if necessary. And in addition, I'm planning to hold at least one office hour, and Monday is the best day for me to do that. And I'm completely flexible other than from 4 to 5 where I have a meeting. So, what time would work? We have a huge class, so that may not work, but who can't do it from 9 to 10? One person. From 10 to 11? 11 to 12. Okay. So, and afternoons, most people have TA. Noon to 1, who can't do it noon to 1? Oh, noon to 1. Bring your lunch. Okay.
This is on Wednesday?
Monday.
Oh, Monday.
Monday. Monday, noon to 1.